Hello, my name is Wyatt and today I'm going to be talking about water flow prediction modeling, a challenge that I've been exploring during my internship this summer with the Agate Institute. I'll be discussing the need for water flow prediction modeling in agriculture, as well as projects I've worked on in my research group. A little bit about me. I am currently an undergraduate student at Washington State University, pursuing a degree in computer science. In 2018, I graduated from Washington State University with a Bachelor of Science in Biology. This summer I've been working with Dr. Janet Dopa and his research assistant Muhammad Amin Garsalui. So, what exactly is water flow modeling and prediction? The goal of our research is to use water flow data from numerous sensors found within the Columbia River Basin to create a model that can make accurate predictions about water availability in future years. The reason this is important is because if we're able to create an accurate model, then we can use that information to make well-educated decisions regarding water storage and allocation. It would allow us to minimize the effect of what would normally be an unseeable issue and address it before it becomes a problem. The focus of my internship was creating a desktop app for visualizing the data from our dataset. Data visualization is an important component when making any AI model, since these datasets contain millions of entries and it may be difficult to create an accurate model based off of raw data and critical values alone. Being able to see how the data changes over time can help generate a sense of intuition about key components of the data that we can then include in our training model. It allows us to visualize the massive amounts of data we have and actually see if our proposed model is making accurate predictions on training and unseen data. Whether you're looking to test the accuracy of your model and make adjustments, or just trying to view the dataset and look at trends in the data, data visualization allows the viewer to gain new intuition and understanding of a dataset that they might not have otherwise just looking at raw data. I started designing my desktop application with hand-drawn concepts to determine what features needed to be included. Once I had a sense of how the application should look, I researched different libraries available for creating a variety of plots and decided to use Matplotlib. Then I researched different graphical user interfaces, or GUIs, compatible for displaying Matplotlib charts, and decided to use PyQt5 since it has a fairly strong reputation from other users. Before trying to incorporate graphs into my desktop application, I generated them in separate programs to check that they were displaying correctly. One challenge I faced when making these graphs was trying to find a way to organize data so that the runtime for generating a figure wasn't too long. Matplotlib graphing functions don't allow for multiple inputs, so curves need to be graphed onto a figure one by one. To decrease runtime, data needed to be reorganized and manipulated ahead of time so that all the curves could be plotted in what is close to linear time complexity. Since this was my first experience creating a practical user interface, I watched a bunch of different tutorials and read several sources before diving into the front-end components. After a lot of trial and error, the application began to take shape, and I began integrating the plots into the application programming button functionality. Button functionality has been especially challenging when making this application since there's millions of ways that you can design a desktop application. So finding sources that help you with your situation, or even just getting started, can be kind of tricky. It often requires problem solving to combine ideas to fit your exact requirements. Here we can see the current progress of the desktop app. These tabs contain a canvas in which there is a menu bar above. The tools in this menu bar are used to navigate through the figure once we generate it. Down below, we can select which variable to graph on the y-axis, select a zoom in which to start when we generate the graph, as well as a start date. So once we generate the graph, and we'll speed this up so it's a little quicker, we can use the toolbar to navigate through the graph, and we can zoom in on certain sections that we want to look at closer. And once we find a section that we want to look at, we can use the slide tool in order to progress through the data either forward or backward in time. One thing to note that each one of these lines that you're seeing here on this figure are different sites. We have 438 different sites that we recorded or had data recorded from, which you can see here on this map that I imported into this application as well. And as you can see, all of these sites are located in the panhandle of Idaho. The vision statement of the Ag8 Institute states that we envision a long-term symbiotic partnership between AI, ag, and human systems that will produce sustained agricultural productivity to meet future food demands. Waterflow modeling and prediction will be a key component in making sustainable agricultural systems, since water is such a crucial component of these systems. If we can make accurate predictions regarding water availability, we'll be able to make proactive decisions in water storage and planting to keep up with future demand. And the ability to visualize these predictions will allow us to clearly demonstrate and communicate the necessity for said decisions. This concludes my presentation. I'd like to thank Dr. Jana Dopa and Muhammad Amin Garsalui for their support during this research experience, as well as the Ag8 Institute for this internship opportunity. Thanks for watching.